Right. So any question before the class? Okay. Okay, let's get started. One announcement before the class. Last time I told you I have only 3 gigabyte storage for uploading lecture video, right? And I think, that is too inconvenient to you and me, because I have to delete old lectures and upload new one, right? So I decided to use YouTube, right? So if you go to YouTube, I already posted last 3 lectures. Probably check this out with your browser. So what do you have to do? You have to subscribe me, or what? What do you have to do to watch these lectures? I don't know. What do you have to do? So I posted. I did what I have to do, right? And now you have to do your part, right? You search Google. You search with Coset 222 probably. I don't know, Coset 222. Oh, not. Okay, not that lecture. Okay, Professor Gugonje also use YouTube, right? That is why. Coset 222. I don't know. Coset 222. Who is? Gugonje. Professor Gugonje. Okay. Anyway, search this link. I don't know. What do you have to do? Let me copy and place here. Yeah, is it playlist? Yeah, check this out. I don't know. Okay. All right. Let's get started. Last time we were, I think, here, right? So refresh your memory. We are talking about translation of high-level code, right? Translation of this high-level code into machine code, right? This high-level code to machine code, right? And for compilation, you have to go through 4 different sub-steps. Those are pre-processing, right? So better slide this one. Pre-processing, compilation, second step. Third step, assembling. The last one is linking, right? The first step is expanding your program, okay? So replace header file, replace macro with actual numbers, right? And second step, compiler is taking that expanded C code, generate instructions, right? Instructions for specific CPU. And then assembler is taking this out, this assembly code and generate machine code, which is composed of ones and zeros, right? So final step is a linking, right? Linking step, linker is taking your code and the code in the library, right? Some functions, right? Some functions are provided by library like printf, file open close, exit, right? Those are provided by library. So you have to link them together and finally generate executable, right? So these green boxes are all binaries. Okay. So four different steps. So I showed you each sub step, okay, with example, this simple example. Okay. So we were here, I think. So let me finish the remaining the PowerPoint. Okay. So this one, Parkwon, can you please?
Instructions and data are represented in binary. Instructions and data are stored in memory. The CPU fetches instructions and data to execute. Binary compatibility allows compiled programs on worked on different computers with the same ISA.
Okay, thanks. So your program, so this one is a simplified block diagram of computer, right? That is our actual, desktop, the main board, right? So you have CPU and memory, right? So we have two big chips, right? Which is called chipset, but it is very complicated, chip, but its function is very simple, right? Communication medium. CPU wants to talk to main memory, right? CPU wants to talk to many different I/O devices. CPU wants to talk to keyboard, mouse, Wi-Fi module, Bluetooth, right? So those I/O devices. So CPU wants to talk to I/O devices, right? And I/O devices are hanging onto this North Bridge side or this South Bridge side, right? So this chipset is just communication medium between CPU to memory and CPU to I/O devices. Its function is very simple, function, right? So actual hardware is very complicated. So we can simplify this, the computer into this, CPU and memory. We have CPU and memory, okay? So your C program, high-level program, if you compile high-level program, that is composed of instruction. Many instructions, right? Some instructions and memory. Sorry, data. So that is your program. Okay, that is your C program. Your C program is compiled. Okay, then that is represented with ones and zeros, right? And C program, your program, software program is composed of many different instructions and data you want to manipulate. So instruction and data. So what CPU does is very simple. CPU, there are many different instructions, many different 명령어 in Korean, many different instructions, and many data you want to process, right? So CPU is reading first instruction, execute it, and read second instruction, execute it, read third instruction, execute it. While it is executing, some instruction is reading the data from this displays. Okay, that's what CPU does. It is very simple. Again, so your program is composed of instructions and data if you compile it, right? And instructions and data are stored in main memory, right? And CPU patch instruction one by one and execute it. Some instruction is reading the data stored in here. Okay. So very simple. The computer is very simple machine. CPU computer is just reading instruction and execute it. That's what CPU is doing. It is that simple. Computer is that simple, right? Again, computer is reading instruction. CPU is reading instruction one by one. First instruction, execute it. Read second instruction, execute it. Read the third instruction, execute it, and so on. That's it. That's what CPU is doing. Computer is doing. Very simple, right? So, okay, this one, Donguk, can you please?
Can you hear me?
Mhm.
Hmm, sounds good so far, but wait, we're talking about RISC-V, not x86. Then how to generate the RISC-V machine code without a RISC-V machine? You're still able to generate RISC-V binaries on an x86 machine. How? Use a cross-compiler.
Okay, thanks. So this is very related to first assignment, right? Cross compilation. So in this class, we are going to study RISC-V instructions and RISC-V machine code, right? First, so that means somehow you need to generate from your computer, from your desktop or notebook computer. Somehow you need to generate RISC-V instructions and machine code. But we have some problem, right? So take this one as an example. You have a C code, very simple C code, and compile it on your x86 based laptop. Okay, x86 based desktop computer. Then compiler GCC, right? GCC or Visual Studio compiler will give you Intel x86 instruction and machine code. Okay, compile it with GCC or Visual Studio. It will give you x86 instructions. Okay, instructions, orange, and the green machine code. Okay, so assume that you have RISC-V laptop computer. So we don't have RISC-V based laptop computer yet, but assume that you have RISC-V machine. Then you can take the same C code and compile it with GCC, and GCC will give you RISC-V instructions. Okay, RISC-V machine code. But we don't have RISC-V machine. We don't have RISC-V computer. Then the question is how to generate RISC-V instructions and machine code from your laptop computer, from your x86 Intel based computer. That is the question, right? So you can use cross compiler. So what is cross compiler? This one, Kyungtaek, can you please? Kyungtaek, can hear you. Probably microphone. You have to. So audio setting is the problem, probably, Kyungtaek. Okay, Yunshik, can you please? Okay, Samuel, I'll get to you. Sorry, I'll get to you about that assignment. Okay, problem. Okay, so after the class. Okay. Okay. Yeah, Kyungtaek. Yeah, you can fix it later on. That's okay. Yunshik has the same problem, I think. Yeonjae?
Yes, can you hear me?
Yes.
Yes, cross-compiler. A cross-compiler is a compiler capable of creating executable code for a platform other than the one on which the compiler is run.
Okay, so it sounds like little bit, tricky explanation. Compiler capable of creating executable code for a platform other than the one on which compiler is run. So in easy language, cross compiler is generating other CPU's instruction, not your CPU's instruction, right? So this one. So you have only x86 based computer, laptop computer. Then I would say this one, this upper arrow, that is a native compilation, and lower arrow is cross compilation. So you are doing normal compilation. If you don't say anything, you are doing native compilation. So you take this one as the input and use GCC, then it'll give you Intel, right? x86, Intel instructions and machine code. But if you use cross compiler, RISC-V cross compiler, it will give you, even though you use Intel machine, okay, even though you use Apple M1 machine, right? Apple M1. If you purchased latest Mac, computer that has M1 processor inside, that has this one has smartphone CPU called ARM, right? ARM CPU, not x86, right? So if you use cross compiler on Apple M1, then it is generating RISC-V instructions and machine code. Okay, so you can use cross compiler to generate other CPUs, not your native CPUs, right? Other CPUs, instruction and machine code. That is about first assignment. And we are going to use that cross compiler throughout this class because we are going to study RISC-V, right? So RISC-V cross compiler. So this one, Sujin and Sujin.
Can you hear me?
Mhm.
Okay, RISC-V cross compiler. Check out the class web for instruction on how to set up an environment to generate the RISC-V code using Eclipse on Windows. Test generate binary from a RISC-V assembly program with assembler.
Okay, so check out the class page. This one, the first assignment, right? So I'm asking you, I'm asking you to do first one, native compilation. Okay, native compilation, and second is cross compilation. Okay, so native compilation is easy, just to use GCC, right? Your GCC, and for cross compilation, you have to set environment, right? Set environment. That has I'm providing instruction here. RISC-V cross compiler with Eclipse. So you click on this, then you have to install. I think four different software. First one is JRE, Java Runtime Environment. Because I want to use Eclipse, very nice GUI, this Eclipse, right? Eclipse environment. That Eclipse requires JRE, Java Runtime Environment. So you need to first install JRE. Then second step is Cygwin. Cygwin is Linux-like environment on Windows, right? On Windows machine, you want to use a Linux-like environment. That is why I'm asking you to install Cygwin. Then third one is cross compiler. Okay, so you can download it and unzip it. That's it. That is installation. Cross compiler, very simple. So those are RISC-V 32, unknown ELF. Look at this GCC. Where is GCC? This one. GCC. That is RISC-V cross compiler, C compiler. Okay, and CPP. This one. ELF cpp.exe. That is preprocessor. 4 different steps, sub-steps, right? Pre-processing, compilation, assembling, linking, remember, right? So this one, AS, that is assembler. Okay, assembler. And then linker, it does not show, right? So I think if you go down a little bit further by screen captured it, right? Then you can find the linker also. Okay. Then Eclipse finally, right? Nice, GUI environment. So if you install everything, then you can do this. Eclipse. So scroll it down. I think I'm providing, right? I'm providing example code here. C and assembly mix, right? So at the end, you should be able to do this. Okay, let's wait. It takes time. Why? Loading time? Why so long? Okay. So if everything goes fine, let me do this. So you create project. Okay. So this project. Okay. C assembly mix. Right? C assembly mix. So go Samuel, right? Installation problem. So so what you have to do is I'm providing this assembly code, example assembly code, right? These two are RISC-V instructions. Okay, RISC-V instruction. We will talk in detail about RISC-V instructions. For now, don't worry about that, right? We will go through one by one, very detailed, right? So example, RISC-V instructions and example C code. Okay, so example C code. This function name is 7 segment. Function name is 7 segment, right? And if you go to assembly code, we don't know for sure this instruction, but it seems like, look at this, J, right? Jump. J means jump. 7 seg. So this instruction is actually calling. This instruction is calling 7 seg function, right? This assembly code is calling that function, C function. So to compile that code, simple. You right click on it, then build project. So look at this. It is using assembler, GCC, linker, some command, right, to generate everything. So then at the end, you can check out this compilation output. Remember from here, right? So after compilation, from high level code, right? This hello.c. Then you use GCC. Then it is generating binary, right? Executable. Right? So binary is composed of ones and zeros. It is not human readable code. So somehow you want to make it human readable code, right? To see what kind of instruction compiler use to compile this code, right? So to get that human readable form of the code, translate back to human readable form, you can use object dump command, right? That command, obj dump, right? Obj dump. So go to Eclipse. So look at this. We use object dump here. Okay. Object dump to translate the final binary lab code into some human readable form of the code. Lab code.dump. Right? So you can check out this dump, right? To see what kind of instruction compiler used to generate your code. Search with 7 seg. Look at this. Look at this. 7 seg, right? Source code 7 seg. Simple code, right? Unsigned int something while statement, right? Return, right? Look at this. Unsigned statement, while, so on, right? So you can see what kind of instructions, right? What kind of instructions compiler used to generate instruction from C code. For example, this opening curly bracket, right? 7 seg, this opening curly bracket is translated into, look at this one, add I instruction, SW instruction, and add I instruction. So 3 instructions. Compiler used these 3 instructions to translate this opening curly bracket. And how about this unsigned int? Unsigned int, this statement, C statement. So compiler used LUI, add I, SW instructions. Right? And how about this? That is also three instructions. LW, LI, SW instructions. Okay. So C statement and what kind of instructions compiler used to generate that, the corresponding statement, right? Okay, so that is the one. So if you compile, if you clean this project, then clean this one project. Okay, and everything will be cleaned. So check out this make, right? Make file. It automate compilation process, right? It has all the command. So going back to Samuel's question. So after you install cross compiler, you have to change this one, home, right? So it depends. This path depends on the path you unzip this cross compiler, right? So at the final step, So step number 4. Okay, here. So after downloading this cross compiler, I unzipped it, right? Unzipped it here, somewhere here, right? And the path. So you have to remember the path where the compiler is located. Okay, compiler is located. So you have to change this path. Okay, that's what you have to do. So it depends on your machine's, the path, right? Your installation path. Right? Any question about this? Okay. Okay, here is the one. Then I think final slide. Okay, the last one. Samuel, can you please? Microphone problem probably. Okay, Konhu, can you please?
Can you hear me?
Mhm.
Yeah. In this course, you need to write some or many RISC-V assembly programs. Use RISC-V assembler to assemble your program and a linker to generate executable. You will also use preprocessor and compiler to generate assembly code from single C code. The compiler course hopefully covers detail about pre-processing and compiler, and assembler, linker, and loader. Then run your code in the RISC-V simulator called Jupyter. Also run your code on the CPU you will design later. We are going to go over RISC-V instructions in great detail.
Okay, so thanks. In this class, probably you have to write some assembly program, RISC-V assembly program, right? And then we have some problem. Even though you write some RISC-V program, the question is how to run that program, because you don't have, right? You don't have RISC-V computer, right? So even though you write RISC-V assembly program, you cannot run it, right? So after midterm exam, I'm going to ask you to design RISC-V CPU. Then that CPU is able to execute the program you are going to write, this assembly, program. But before that, right? Before midterm exam, how can you run your, RISC-V program? Okay, there is a way you can use this simulator, RISC-V simulator called Jupyter. I'm going to explain this RISC-V simulator, okay, later on, not today. But you can think of it as a RISC-V CPU. Jupyter is RISC-V CPU. So it is able to take. So somewhere in memory, you store RISC-V instructions and some data you want to process. Okay, so Jupyter is able to take those instructions, it can execute it. Right? So you can think of it as CPU, okay, RISC-V CPU. In the meantime, right? Before midterm exam, we are going to use Jupyter, but after midterm exam, you can use your own CPU because you are going to design CPU, right? Later on. So that will be very interesting, right? So you design CPU, right? Then your program is going to be run on the CPU you are going to design. Okay. It's like you are a god, right? You are a creator. You are creating everything from bottom up, right? CPU, system. Then your program is running on top of that, right? It's very fantastic experience actually. Okay, that is about the first this lecture. Any question before switching to next one? Okay, let me. So if you open up the first assignment again. Let me give you some more instructions, right? So what I'm asking you to do is use this C code, right? So compile this C code, okay? This to compare. So what you have to do is, after setting up this Eclipse environment, you can just replace. You can just replace this 7 segment, okay? 7 segment with this code. Simple, right? Replace, right? Replace this part, this code with that. Okay. Then change. Okay. Change this jump 7 seg, right? To jump, what? Jump compare, right? Jump compare. Jump compare. So assembly code is going to call this compare. That's it. Then press that button. Press, build project. Okay. So let me show you like this. What you have to do is like this, right? Then assembly code, compare like this. Then build project, right? Then open up this labcode.dump and check this function, right? To see. Look at this. So this opening curly bracket is translated to 1, 2, 3, 4, 5 instructions. Okay. This code. Okay. This statement, C statement. Look at this, right? This C statement, right? Min. A is equal to min, B, and C. Right? That got translated into 1, 2, 3, 4, 5, right? 5 instructions, right? And so on, right? Okay. That is about first assignment, simple. And one thing you have to be careful for native compilation, okay? 1, 2, 3 sub-bleach. Here, 1, 2, 3, 4 sub-bleach, right? So cross compilation, you go through a linking step, but native compilation, you cannot go through linking step. So why is that? Why? Because you don't have a main function, right? Think about hello world program, very first program. The program you write in C language course. You are supposed to have your function supposed to have what? Main, right? Main function, right? Whatever this return type is. So your code is supposed to have a main. GCC is expecting this main, right? But in this assignment, we don't have a main function, right? We don't have this main function. We have only compare function. So linker will fail, right? So I'm not asking you to go through the final stage, okay? For native compilation, okay, only 3 steps. But cross compilation, 4 different steps, okay, 4 different steps. Okay, let's move on. Okay, now, guys, we are not going to cover this lecture 3 because of time limitation. So according to my teaching experience, the computer architecture course experience, we don't have enough time to cover all these lecture slides for one semester. Okay, and even worse, next week is Thanksgiving holiday, right? So that means no class during next week, right? So we don't have time to talk about everything, right? So we are not going to we are going to skip less important PowerPoint and focus on very important, lecture slide. So we will talk about lecture 4 directly about RISC-V instructions. Okay. So click on this. Okay. Okay, so RISC-V instructions. This one, Yunsu, can you please? Microphone problem? Can hear you.
Hello,
Okay.
can you hear?
Yes. Yes.
CISC, complex instruction set computer. One instruction does many jobs. Example, mobs in x86, variable length instruction. Examples, x86, Intel, AMD, Motorola 68K, RISC, reduced instruction set computer. Each instruction does a small unit job. Example, add LWSW BQ in RISC-V. Fixed length instruction, load store architecture. Example, RISC-V, ARM, MIPS.
Okay, thanks. There are several ways to classify computers. Okay, so last time we classified the computer, like personal computer, server computer, and embedded computer. That is one way of classifying computers. Okay, and CISC, this one, CISC and RISC division is another way, actually very classic way of classifying computers, right? CISC computer and RISC computer. So x86 is the best example of CISC machine, and MIPS, ARM smartphone CPU, and RISC-V are examples of RISC computer. As the name implies, right? CISC stands for complex instruction set computer. Each instruction is very complex. CISC, right? Complex instruction. Each instruction, one instruction is doing many complex jobs. Whereas RISC machine, each instruction is doing very small job, super small job. Okay, so let me give you a concrete example. Okay, so in Intel computer case, CPU, we have memory. Intel is providing. So one good example is Intel is providing this instruction called move string. Move string. Okay. So that means what? So one example is you want to copy H hello, HELLO from this location. For example, 100. Memory location is 100. From this location, you want to copy to destination. Okay. HELLO. Okay. From here, let me call this source location. Source or location, right? Address or location. From this source location 100, you want to copy 5 characters to this destination. Destination location. Okay. Assume it is 200. Location 200. Okay. And then the thing is, this one instruction is doing this copy operation. One instruction, one machine code is able to do this copy H to here, E to here, L, so on. This copy operation. Let me explain how complex this is. To execute that instruction, first you have to set some registers. Okay. Don't worry too much about this register, this terminology. We will talk in detail about that. Okay, later on. So inside the CPU, inside x86 machine, you have register called source index, source, right? Source index, and you have register called destination index, destination. Okay, destination, and then CX register, that is called count register. That means it is count register. So what you have to do before executing this code to copy from here to here? So you have to set source location. Okay, that is 100, 100. It is pointing that location. And you have to set destination index register to 200. Okay, that is pointing then this location. Then how many characters? How many characters you have to copy? 1, 2, 3, 4, 5. HELLO. So 5 here. Count. Then boom, you have to execute. You execute move as instruction. Then what would happen? Then what happens is CPU is reading. CPU is reading first character. Reading first character. Then store that into this destination location. Okay. So first character just copy it. After that, CPU is doing incrementation. Okay, so we are done with the first character. So that source location is incremented by 1 to 101 to point next location. So 10, okay. So 100, this one, 101 location, 102, and so on, right? Okay, here 200, this next location, 201, 202, and so on. Okay. So then not only this source location, but destination location also incremented to 201 to point next location. And then count register, count number. Okay, I just copied one character. So this count register will be decremented by 1 to 4. Okay, 4 characters remaining. Right? So then CPU. So after doing addition and subtraction, 101, 20, addition, right? And subtraction, 5 to 4. Then next location, right? E is read, stored inside the CPU, and that is copied to, that is stored to destination location. So second character, copied. So afterwards, CPU is doing the same thing, right? So source location is incremented to 102, 202, decremented. Okay, 3 characters remaining. So it is doing, CPU is doing that operation 5 times to copy 5 characters. Okay, HELLO. Then that will become 0. So CPU will check exit condition. So this count register becomes 0. Then CPU is done. Okay, I'm done executing move S instruction. That is happening inside the CPU. It is very complicated operation. To human, okay, just copying just 5 characters to destination. Is it that complicated? To human, it is not, but to machine, CPU, very complicated operation because you have to copy, store, read, write, okay, increment, decrement, check exit condition. All operations are done by digital logic, not human, right? So that is, the CISC machine. One good example. One instruction is doing very complicated, very complex job, right? Read, write, increment, decrement, check, exit. I'm done or not, right? Very complex operation. Whereas risk motion case, there is a separate instruction for that operation, read operation. Okay, this read operation, separate instruction called read, LW, memory read, load instruction. And separate instruction for this write operation. Okay, write operation. okay, called SW, store instruction, memory, store instruction. And separate instruction for this addition, right? RISC-V case, you have ADD instruction, addition instruction for this incrementation. And also separate instruction for subtraction, SUB. So for RISC case, to design, to copy, 5 characters from source to destination, you have to write program with this one LW, SW, add, solve. Okay, with those instructions, you have to write program. Okay, so that is RISC machine. Okay, RISC machine. Each instruction, right? LW instruction is doing very, unit, very small, operation, just reading from memory location. SW instruction, simple, right? You are writing this data to, memory location. That's it. That is the role of store instruction, right? Addition instruction, just incrementing, right? Incrementing +1, incrementing, right? Okay. So, CISC computer, like Intel computer, Intel CPU is super complicated because Intel x86 is providing, CISC instructions. Each instruction is doing, very complex job. So hardware design, the CPU design, right? CPU design is very complicated. Whereas RISC CPU design itself is simple. I would say very simple. Okay. Then which architecture is better? CISC is better or RISC is better? There is a debate about that issue. Okay, in 1980s, people was fighting. Okay, CISC is better. Some people said, okay, no way, RISC is better. But these days, these two architectures live in peace. No one is fighting, right? Intel still x86 still providing CISC instructions, and RISC-V, ARM, MIPS CPUs are providing RISC-based instructions. Okay. Any question about this? So advantage, right? Advantage, disadvantage. The CISC case, disadvantage, is hardware complexity. Hard CPU is very complicated, whereas memory footprint, right? You want to copy from the source location to destination. One instruction is doing that operation, right? So memory footprint, your program size is going to be very small because one instruction, one machine code is doing that operation. Okay, program size. So bad thing, CPU complexity. Good thing, program size, right? Whereas RISC, bad thing is CPU. The program size is big because you have to use many different instructions to implement same function, copy operation, right? Memory footprint. The program size is bigger. But good thing is CPU. CPU is going to be very cheap because simple. You can you use a small number of transistors to design CPU, right? So it is going to be cheap. Okay, so this one. User one.
Free and open RISC ISA. Emerging ISA with active participation from academia and industry. 32-bit, 64-bit, and 128-bit feature architecture versions. We study a 32-bit version.
Okay. Some introduction about RISC-V. It is open instruction set. So they are opening this consortium. RISC-V consortium is opening the instruction set. Okay, RISC-V is supposed to provide, this add instruction, sub instruction, add instruction, sub instruction, LW stored, and so on. They open, so no royalty. So if you want, you can design CPU, you can sell CPU free of charge. But in case of smartphone CPU, ARM, okay, you have to pay, a lot of money to get a license, okay, from ARM. So, good thing about RISC-V is free. So there are several startup companies designing and selling, RISC-V CPU because it is open. Okay, so it is also emerging. It is gaining a lot of traction these days, right? So it is ARM and RISC-V. Before RISC-V, before RISC-V architecture, before RISC-V architecture was open, ARM was dominating the market, ARM. So everyone is using ARM, but these days, ARM get, so the RISC-V is emerging, and so the ARM is get pressure, okay, because they are RISC-V is gaining some market share, which is used to be occupied by ARM. Okay, so it is gaining a lot of traction. So good to study RISC-V. So also if you Google search with RISC-V, RISC Android probably, Android wiki page. So I found that, look at this Android wiki page. Then scroll it down. So it says, look at this. So platform, the Android is supporting ARM, right, and x86 and RISC-V. Okay, RISC-V CPU as well. So who knows, right? You will see some RISC-V based smartphone later on someday. Okay, so for now, RISC-V is supporting 32-bit architecture and 64-bit architecture. 120-bit is not released yet. So I think it's too big architecture for now. So in this class, we are going to study 32-bit architecture. Okay, this one. 송민주. Microphone problem. Okay. Isn't it good to design CPU if one instruction does many jobs? Okay, Yongsub's question, isn't it good to design CPU if one? Yeah, Yongsub, problem is, CPU complexity. Yes, okay, it's okay. Yongsub, CPU complexity. Because one instruction is doing very complex, job, right? Then CPU's design is going to be super complicated. Think about that. That is done by digital logic, right? Copy operation, okay? Addition operation, subtraction operation, and exit condition check, all done by CPU digital logic. So CPU is going to be super complicated design. Think about that. You are designing Intel, CPU, right? Supporting, move as instruction. Then what do you have to do? Right? Very complicated, right? So that means the CPU is going to be very big, okay? Using a lot of transistors. That means it's going to be expensive. And also, dissipating a lot of power. Power consumption is the problem because, you are using a lot of transistors. Okay, so RISC-V, it is essentially providing 4 base instructions. 32-bit architecture is called RV32I. RISC-V 32-bit. I means integer instruction. It is supporting integer, right? Integer. in Korean 정수, right? Not floating point, right? Integer operation. In C, if you think about C code, right? A, B, C. A is equal to B plus C. So you can execute this kind of code. It's integer, right? A, B, C, integer. For example, 1, 2, -5, those numbers. Integer operation, not floating point operation. If you use floating point, if you want to do floating point arithmetic, then you have to use, right, this keyword, A, B, C. Okay? A is equal to B minus C. So A, B, C can be like 1.2 or 2.43 and so on, right? Something like that. Not floating point operation, but integer operation, 정수, right? In Korean, 정수 operation. Okay. 64-bit architecture is called RV64, right? RISC-V. 64 integer. So there are two big architectures, 32-bit, 64-bit. And sometimes, you know, the instructions RV32I is providing is not enough. Sometimes it is only supporting, you know, 40 RV32I. 32I is providing only 40 instructions. 40 instructions. You know how many instructions Intel is providing? If my memory is correct, it is providing 1,500 instructions. Roughly 1,000, more than 1,000 instructions. Whereas, look at this, RISC-V is providing only 40 instructions. Okay, so you know these 40 instructions may not be enough to run your application program for performance, you know, with good performance. So they are providing some extensions, right? So M extension, A extension, those instructions. So if you want, in addition, those are, you know, required instructions you have to support. 32-bit architecture, if you want to design 32-bit RISC-V CPU, you have to implement CPU. Okay, you have to implement CPU supporting all of these 40 instructions. Okay, and extensions are optional. If you want, you can add M extension. If you want, if you can add A extension, it is required. Those are optional. Okay, so M extension is providing multiplication and division instructions. So that means RB32I, okay, it is providing only addition and subtraction. Very simple, right? And if you want to do multiplication and division, okay, you can add, okay, I need to implement M extension. Instructions M extension is providing in addition to RB32I. Then you can call it RB32I M. Okay, my CPU is able to execute instructions. Those instructions, RB32I M. Okay, I, okay, and M extension. Support A extension, then you can say, okay, I am A atom instructions. Okay, so mandatory instructions, required instruction, those are optional instructions. Okay, so in this class we are going to focus on only these mandatory instructions. Okay, RB32I is supporting. Okay, so this one, I guess RISC needs more instructions than CISC to perform well, equal to CISC, isn't it? Hijin, not really, because think about that, right? In CISC case, right? CISC case, it is very complicated because, you know, instruction is very complicated because you want to do, you know, okay, so how to explain? In CISC case, So CISC, camp is trying to support some semantics, some function semantics. I would say function, right? So something is this. Example is string copy, right? Move as. So in C code, probably you can use str string copy instruction. String copy API. String copy, right? String copy API to do that, copy operation from this source location to this destination. And CISC camp is trying to, support that function, right? That function in instruction with one instruction, string copy. But think about that. How many different, APIs? How many different APIs? Application programming interface. How many different APIs? Libraries providing. And then you have to provide separate instruction for second function, okay? And third, this, API with separate special, special instruction. So, there are a lot of APIs. Then CISC architecture is trying to support those many different APIs with one instruction. So there are, a lot of instructions. Right? There are a lot of instructions, 1,500 instructions, right? Whereas risk case, it is not, risk is not providing those complex instructions. This complex operation can be designed with combination of many different unit instructions like LW, SW, add, sub, and some instructions. By combining these, different instructions, you can implement this function. Same thing for this instruction. You can use the same instruction by combining. By mixing those instructions, you can provide this function. Also, same by mixing those instructions, you can provide the same this function. Right? Yes, right. So risk is providing only those few, that dozens of instructions. By combining those dozens of instructions, you can implement many different functions, right? Whereas CISC is trying to support many different functions with separate instructions. That is why you have so many different instructions in CISC, right? Okay, Hijin, can you please? Microphone problem? Okay. Q1?
Instructions. Let's discuss what kinds of instructions are essential to CPU. Instruction categories. Data processing instructions, arithmetic, and logical. Memory access instructions, load store, branch instructions.
Okay, thanks. We are going to study now. From now on, we are going to study RISC-V instructions one by one in very detail. But before that, I like you to think. About the instructions. What kind of instructions CPU should provide for CPU to be CPU, for the CPU to be CPU. Then what kind of instructions CPU should provide, CPU should support? I like you to think, right? So the thing is, first, why do you want to use computer? So that is simplified, computer block diagram, right? You have CPU memory. The reason why we want to use computer is because, computer is doing arithmetic or some arithmetic operation, right? This one, addition, subtraction, multiplication, division, those arithmetic operation. Computer is able to do those arithmetic operation super fast. Okay, in 1 second, for example, if CPU is running at 1 gigahertz, that means in 1 second, CPU can do 1 billion, roughly 1 billion additions. Okay, one gigahertz. This clock, right? Clock is 1 nanosecond. Clock period. So you have 1 billion pulses in 1 second. That is the meaning of 1 gigahertz. That is the meaning, right? Within 1 second, right? Within 1 second, you have 1 billion pulses. So within this time, computer is able to do one arithmetic operation. So super fast, right? So in 1 second, 1 billion operations. In Korean, 10억 operation, 10억 addition, 10억, 1 billion additions per second. Very fast. That is why we want to use computer. This guy is very, good, super good at, arithmetic operation. Okay. So the first category of instructions CPU should provide is data processing operation, right? So data processing, addition, subtraction, multiplication, division, those, data processing operation. Okay. And second category of instructions is memory access instruction, right? I told you, right? Your program is composed of a lot of instructions, many different instructions, and data you want to process, right? Initially, those are stored in memory. That is your program. Okay, instruction and data. So those are stored in memory, right? So to do arithmetic operation, okay, example, to do this kind of arithmetic operation, okay, so you have to copy, you have to bring in this P data, right? So you have to bring in this data B and C. Okay, I have to place that inside the CPU B and C to here. Okay, so after then, arithmetic operation is arithmetic operation. CPU will do arithmetic operation. And then afterwards, after doing arithmetic operation, you have to update A, right? Which is here. So addition output, B plus C output will be stored somewhere A. Okay, final output will be stored back to memory. So to manipulate the data, to process data, you have to copy this data to, to some place inside the CPU. Then CPU can do, arithmetic operation. So place B and C, in this case, B and C somewhere in CPU, which is called register. Okay, register. Place B and C into the register. Then CPU can read the B and C, then do arithmetic operation. Okay. The afterwards, after doing arithmetic operation, final output should be placed back to main memory. So read operation, memory read operation, then memory write operation. Okay, read operation, write operation, which is called memory access instruction. So you have to access memory to place B and C into here and store this data to main memory. Okay, so memory access instructions. That is second category of instructions. Okay, the last one is called branch instructions. Okay, so why branch instruction? If you don't have branch instructions, then what happens is, instructions, right? There are many different instructions like addition, subtraction, LW, SW. If you don't have branch instruction, what CPU is doing? CPU is reading first instruction, execute it. CPU is reading then second instruction, execute it. Then third instruction, fourth instruction, and so on. That's what CPU is doing if you don't have branch instruction, right? But branch instruction is changing the location. Okay, after this, BEQ, for example, BEQ instruction, branch instruction. Okay, after this instruction, you execute that code. Okay, do not execute in the middle. Okay, then execute from here. So why? What is the function of branch instruction? In high-level language, think about that. Think about, if statement. If A is equal to B, then you do C++. Otherwise, you do C minus minus. So conditional execution, right? So CPU, okay, execute this code. Okay, these two are equal. Okay, then next instruction. So you can think of it as pseudocode, right? So you have if A is equal to B, then next code is C++, and next code is C minus minus, C minus minus. So you need to check the condition, right? If this condition is met, A is equal to B, then next is okay, execute it. But A is equal to B, then you should execute next instruction, C++. But what if this condition is not met? These two are not equal. What do you have to do? You have to skip this part, then execute C minus minus. So look at this, condition is not met. This condition A is not equal to B. Then what do you have to do? Okay, do not execute, skip this part and execute next one. Okay, for that purpose, not only if, I think about that while statement in C. Also for I is equal to 0 until 100, then you do some operation, B plus 1 and so on. So this conditional execution, you are checking the condition. Condition is met, you keep executing the code in the body. Otherwise, you skip. Okay, do not execute. Okay, condition is not met, you skip the body of this for loop, then execute next instruction. So for conditional execution, CPU is providing branch instructions. Okay, that is important thing. This is important thing. Every CPU is providing these three categories of instructions. Intel x86 is providing data processing, memory access, branch instructions. Smartphone CPU, same thing, right? Smartphone CPU, ARM, is providing data processing, memory access, branch instruction. RISC-V, same thing, right? RISC-V, data processing, memory access, branch instructions. So if you don't support these three categories of instructions, that is not CPU. That is not CPU, okay? The other instructions, okay, CPU, depending on CPU, some CPUs are providing some advanced instructions like MoveS, right? MoveS, and those instructions are performance to providing some good performance. Okay, and something like, so the other example is the encryption instruction like AES, right? AES encryption, right? If you are interested in security, right? Data security, you use that kinds of algorithm to encrypt your data, right? Okay, encrypt. And Intel CPU, smartphone CPU is providing instruction. This is the assembly instruction for encrypting your data. So without that instruction, you have to write very long, very long C code. But these days, one instruction is doing that operation. Okay. So the point I'm trying to make is CPU. Every CPU is providing these 3 categories of instructions, and some CPU are providing some miscellaneous, some auxiliary instructions for performance reason. Okay, but these are mandatory. Every CPU should provide, right, mandatory instructions. So you have to have this big picture. Okay, and we are going to study the instructions belonging to data processing, and some instructions belonging to memory access, and instructions belonging to branch instructions, starting from data processing. Okay, how do these categories apply to CISC? Can one instruction have multiple categories? Yes. CISC case, right? CISC case, right? Move as instruction. Good question, right? Move as instruction, which category? Move as instruction, it is doing, memory read operation. Right? Move as instruction is doing second category, memory read operation, memory write operation, and also arithmetic operation, data processing, right? Addition, subtraction, right? Also check the exit condition. You can think of it as branch, not branch, but exit condition, right? So CISC case is CISC case, CISC instruction. It is not clearly separated. Okay, so that means move as instruction is not belonging to data processing, not belonging to memory access, not belonging to branch. Combination of data processing and memory access. CISC, right? That is why CISC instructions are complicated. Okay, but yes, risk case, there are separate instructions for data processing, separate instructions for only memory access, separate instructions for branch. Right? That is a risk machine. Okay. Okay, I think we have to stop. We have to stop here. Time is up. Any other questions? So on Wednesday, today, we will talk in detail about RISC-V instructions one by starting from data processing. So it will be very interesting. It will be very interesting. All right. That's it. That's it for today. Yep. Thanks. I'll see you.
Professor,
Mhm.
can I ask something about the assignment?
Okay. Sure.
So for this assignment, I set up all the environment for the cross compiler.
Mhm.
저 혹시 한국어로 해도 괜찮을까요? 아니면 계속 영어로?
아니, 끝났으니까 한국어로 해도 돼.
아, 감사합니다. 덤프 파일에 지금 그 각 과정들의 아웃풋들이 다 존재하는 건가요? 아니면은 그 각각의 뭐 .5 파일이라든지 이런 식으로 과정별로 아웃풋이 나오는 파일들이 다 따로 존재하는 건지. 왜냐하면 사실 그 인스트럭션에 보면은 이제 unknown ELF 해가지고 이런 그 명령어들을 각각 다 따로 사용하라고 되어 있는
그치.
느낌이었는데
맞아.
어떻게 해야 될지를 잘 모르겠어서.
그거를 이제 좀 고민을 해보라는 건데, 숙제에서는 그 메이크 파일에 비밀이 있거든. 메이크
네네.
파일을 아마 여러분들이 아직은 그 2학년 학생들이기 때문에 메이크 파일이라는 거를 많이 안 사용해 봤을 것 같은데, 메이크 파일은 그 예를 들어서 뭐 여러 그룹에서 만약에 하나의 애플리케이션, 아주 큰 애플리케이션을 프로그램을 한다고 하면 소스 코드가 뭐 한 1000개가 있어. 1000개를 우리가 뭐 바꿀 때마다 일일이 다 하나씩 컴파일해서 다 이제 링킹해서 1000개를, 그래서 최종적으로 오브젝트 코드를 만들면 굉장히 번거로운 작업이거든. 언제 하나씩 GCC A-C -O A, 그다음에 또 두 번째 코드 컴파일, 세 번째 코드 컴파일, 그걸 손으로 치면 얼마나 그거 힘들겠어 그걸. 그러니까 이제 make 파일이라는 거를 사용하면 그거를 전체를 오토메이션 시켜주는 거거든. 여기다가 그 인스트럭션을 적어 놓는 거야. 컴파일하는 스텝을. 그러면 그냥 여기서 이클립스 하는 것처럼 빌드만 해주면 지가 알아서 1000개를 쫙 컴파일하고 그 다음에 최종적 바이너리를 만들어주는 거지. 그래서 여기 한번 이 어떤 인스트럭션이 있는지 이 make 파일이라는 것도 제대로 이해하려면 이 책으로가 있거든. make 파일, make utility라고 책이 있어. 그걸 봐야 되는데 여기서는 뭐 그냥 간단하게 인투이티브하게 대충 봐도 알 수 있도록 그냥 적어 놓은 거니까. 그치? 그러니까 예를 들면 얘를 컴파일 하려면 얘와 얘가 필요하다. 컴파일 할 때는 이런 과정을 거쳐라. 그치? 요거와 요거를 갖고 최종적으로는 이게 나와야 된다. 근데 LD가 뭐냐면 여기 있지. 요 링커를 써라 라는 거지. 그다음에 여기 다 사실 코멘트를 해놨지. 여기서 코멘트 아웃을 시키면 이렇게 시키면 이제 되겠지. 사실은 뭐 프리 프로세서 C 코드 얘를 컴파일 하려면 이 C 코드를 인풋으로 사용해라. 여기서 그러니까 요거 고쳐야겠네. 그치? 7 세그먼트 다 C로 고쳐야지. 그러니까 CPP는 뭐야? 보면 프리 프로세서지. 이게 프리 프로세서 CPP. 그러니까 얘를 써서 고쳐야겠지. 이렇게 7 세그. 출력은 뭐 그냥 이름 똑같이 하지 뭐. 분 세그. 요걸로 해라. 그러면 이제 프리 프로세싱의 출력이 나오겠지. 다 가르쳐 주네. 그 다음에 컴파일레이션. 그 다음에 입력은 지금 방금 만든 7 세그. 요거 얘를 입력으로 세그. 이렇게 하면 이제 .s 파일이 나오겠지. 아마. 이렇게 하라는 거야. 요걸 갖고. 누가 지금
감사합니다.
답까지 다 알려줬네.
이해가 너무 잘 됐습니다.
오케이. 그러니까 여러분들이 이 메이크 파일 이게 이제 회사 가면 회사까지 갈 필요 없고 사실은 뭐 이제 고학년이 되면 이제 규모 있는 프로젝트를 할 때 메이크 파일이라는 걸 사용하거든. 많은 사람들이 같이 개발하거나 혼자 개발하더라도 여러 개의 뭐 C 파일이 있잖아. 예를 들면 뭐한 20개 파일을 개발한다. 모듈러하게 해서. 그러면 그걸 매번 GCC 컴파일 또 두 번째 파일 컴파일 하고 나중에 다시 뭐 언제 하고 있어 그걸. 그치? 한 번에 그냥 오토메이션 시켜야지. 오케이. 성필. So complicated instruction is CISC implemented in hardware, while RISC we should implement the same. move S 같은 예를 들면 만약에 move S 같은 걸 아까 CISC에서 그거를 리스크 머신에서 만들고 싶으면 프로그램을 짜야지. 그렇지? 그 카피 H를 카피하는 코드. 그다음에 뭐 두 번째 캐릭터 카피하는 코드. 5개 다 카피했나? 그거 체크하는 코드. for loop 같은 걸로. 엑시 컨디션. 그러니까 리스크에서는 그런 펑션으로 여러 개의 기본 단위의 인스트럭션들을 조합해서 하나의 이제 기능을 하는 어떤 기능을 하는 그런 펑션을 만들 수가 있는 거지. 하지만 시스크에서는 그런 펑션을 하나의 인스트럭션으로 제공하려고 하는 노력을 하는 거야. 그렇지? Then risk takes more time to perform same. Yes. 시스크는 프로그램 사이즈가 작지. 왜냐하면 아까 그 move s라는 걸 생각을 해보면 스트링 카피, 그렇지? C에서 이 스트링 카피라는 그 API를 뭔가 뭐 코드가 좀 더 붙긴 하겠지만 이센셜하게는 얘 하나의 인스트럭션으로 하나의 머신 코드로 구현이 되는 거기 때문에 그치 하나의 머신 코드로 구현이 되는 거기 때문에 이게 이제 메모리에 move s만 있으면 돼. move s 코드 move s 인스트럭션 하나만 있으면 돼. 하지만 그러니까 프로그램의 사이즈가 작은 거지. 이 스트링 카피를 하는 프로그램 이거 하나로 카피를 한다고? 된다니까 그게. 근데 시스크에서는 여러 개의 인스트럭션들을 조합해서 여러 개의 인스트럭션들을 막 조합해서 같은 펑션을 구현하는 거니까. 오케이. Other questions?
Professor, yeah, in today's class, you said that we cannot do linking step in native compiler,
Mhm.
and we can do cross compiler because of main function. So
그치, right. Main
can I
function is
know?
not present, right?
Yeah.
Why? Why is the
yeah,
why?
yeah.
Right. GCC, right? So if you compile it with GCC, right, on Linux machine or Windows machine, compiler is expecting. Compiler is expecting. Let me do this. Hello, that's it. For example, here, right? You have a main function, right? So let me compile this code here. So here, I already compiled it, right? Remove hello. GCC, right? Hello, that's C. I want output to be hello. Compiles okay because you have main function. But if you change this one to compare, for example, right? Try to compile it, right? Undefined reference to main. So compiler GCC is expecting the function name main, right? In native compilation. So that is a protocol, right? Protocol, right? When you write a application program, so main function is the top file, right? So inside the main, you can have many different other functions inside, right? But at least top file, you should have a main function. Otherwise, compiler refuses to generate the final executable. So Linux runtime is expecting this label. Is it answering your question? 누가 질문했지?
네, 제가 질문했습니다. 감사합니다.
그러니까 메인 펑션은
네.
여러분 아무 생각 없이 썼지만 그동안
음.
메인 펑션이 있어야 돼. 그러니까 이제 비주얼 스튜디오로 개발하거나 뭐 리눅스에서 그 엑셀에서 돌아가는 프로그램을 개발할 때 메인이 없으면 컴파일이 안 돼. 얘네가 메인이 없다고 나오거든. 프로토콜이야. 이게 우리 메인은 있어야
근데
돼.
그게 혹시 링킹 스텝에서만 해당되는
그치?
얘기인 건가요?
맨 마지막
GCC가
스텝.
링킹 스텝이었어요?
맨 마지막 스텝에서 그렇지, 링킹 스텝에서
네.
이제 그 리눅스 머신에서 실행할 수 있는 파일을 만들 때지. 그러니까 링킹 스텝이 실행할 수 있는 파일을 만들 때잖아. 실행 파일, 맨 마지막에 실행 파일.
네.
근데 메인이 없으면 리눅스 OS에서 혹은 윈도우즈 OS에서 실행을 못 하거든. 얘가 그 레이블이 있어야 돼. 그 레이블이 없으면 얘는 실행을 못 해. 그러니까 프로토콜이라고 내가 얘기하는 게 약속이야, 약속. 프로그램 짤 때 메인은 무조건 있어야 돼.
그렇군요. 이해됐습니다. 감사합니다.
Okay. Other questions? 메인 펑션을 줘야 되고. 메인 펑션 줘야 돼.
교수님, 교수님 들리시나요?
들려.
제 과제에 메인 펑션을 처음에 오류가 나가지고 추가해서 이제 과제를 다 했는데 보고서에 추가한 코드를 같이 첨부해서 작성해도 괜찮을까요?
그래도 상관없지. 그렇지? 뭐 여기 숙제 펑션 네임은 컴페어지만 그리고 굳이 여기서는 마지막 스텝까지는 뭐 하지 않아도 된다 그랬잖아. 어셈블링 스텝까지만. 그 다음에 링킹인데 나는 근데 링킹
네.
스텝도 보고 싶다. 그래서 메인으로 바꿨다. 오케이, 그래서 오케이지 뭐.
처음에 그걸 해야 되는 줄 알고 이렇게 만들었는데 하고 보니까 그렇게 해가지고 코드가 좀 긴데 같이 첨부해도 괜찮은 거죠?
그렇지.
네, 감사합니다.
Okay. Other questions? Okay, how many? 32. Okay, see you. CPU. What is the difference for the speed and CPU? What is the difference, for example, between speed and architecture? Samuel, I think the question is a little bit strange. 1 gigahertz is operation frequency, right? So let me try to explain your question. So speed has nothing to do with the frequency has nothing to do with, you know, I would say nothing is not nothing. That is not, you know, 100% correct description. But architecture, when you say architecture, 64-bit architecture, right? That means a data path, right? So inside the CPU, I think last time I told you, right? Inside the CPU, you know, simplified CPU the block diagram, right? You have register and registers and ALU that is doing all arithmetic operation. This ALU takes 64-bit data, and generate 64-bit output in case of 64-bit architecture. That is architecture, right? So architecture is a basic unit. That means, in other words, basic unit of data processing. Data processing is based on 64-bit. In other words, we call this data path. Data is traveling through this path, right? Data path width is 64-bit in size. That is the architecture. And 1 gigahertz means it's one operation. So we will talk in detail about, you know, this 1 gigahertz. 1 gigahertz means what? 10 to the power of 9 hertz. Okay, 1 billion, right? Essentially. So that means T clock, you know, period T. You have how many? Within 1 second. Within 1 second, you have 1 billion of them. 1 billion, right? So in this, if I link, you know, this one and this one together, within this one, within this, you know, T, within this time, in this case, this time is 1 nanosecond. So within this time, you can do one arithmetic operation. One arithmetic operation. Take these two as an input, generate output. That whole operation, read the data from here, and do some arithmetic operation and write to here. That whole operation is done within this 1, you know, nanosecond. Okay, Samuel, that is answering your question. Okay, thanks. Any other questions? Okay, then see you on Wednesday.